Backpropagation is a really big word, but it's not a really big deal. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about Neural Networks Part 2, Backpropagation, Main Ideas. Note, this StatQuest assumes that you are already familiar with neural networks, the chain rule, and gradient descent. If not, check out the quests. The links are in the description below. In the StatQuest on Neural Networks Part 1, Inside the Black Box, we started with a simple dataset that showed whether or not different drug dosages were effective against a virus. The low and high dosages were not effective, but the medium dosage was effective. Then we talked about how a neural network like this one fits a green squiggle to this dataset. Remember, the neural network starts with identical activation functions, but using different weights and biases on the connections, it flips and stretches the activation functions into new shapes, which are then added together to get a squiggle that is shifted to fit the data. However, we did not talk about how to estimate the weights and biases. So let's talk about how backpropagation optimizes the weights and biases in this and other neural networks. Note, backpropagation is relatively simple, but there are a ton of details, so I've split it up into bite-sized pieces. In this part, we talk about the main ideas of backpropagation. 1. Using the chain rule to calculate derivatives. And 2. Plugging the derivatives into gradient descent to optimize parameters. In the next part, we'll talk about how the chain rule and gradient descent apply to multiple parameters simultaneously and introduce some fancy notation. Then we will go completely bonkers with the chain rule and show how to optimize all 7 parameters simultaneously in this neural network. Bam! First, so we can be clear about which specific weights we are talking about, let's give each one a name. We have W sub 1, W sub 2, W sub 3, and W sub 4. And let's name each bias. B sub 1, B sub 2, and B sub 3. Note, conceptually, backpropagation starts with the last parameter and works its way backwards to estimate all of the other parameters. However, we can discuss all of the main ideas behind backpropagation by just estimating the last bias, B sub 3. So, in order to start from the back, let's assume that we already have optimal values for all of the parameters except for the last bias term, B sub 3. Note, throughout this and the next StatQuests, I'll make the parameter values that have already been optimized green, and unoptimized parameters will be red. Also note, to keep the math simple, let's assume dosages go from 0 for low to 1 for high. Now, if we run dosages from 0 to 1 through the connection to the top node in the hidden layer, then we get the x-axis coordinates for the activation function that are all inside this red box. And when we plug the x-axis coordinates into the activation function, which, in this example, is the soft plus activation function, we get the corresponding y-axis coordinates and this blue curve. Then we multiply the y-axis coordinates on the blue curve by negative 1.22, and we get the final blue curve. Bam! Now, if we run dosages from 0 to 1 through the connection to the bottom node in the hidden layer, then we get x-axis coordinates inside this red box. Now we plug those x-axis coordinates into the activation function, to get the corresponding y-axis coordinates for this orange curve. Now we multiply the y-axis coordinates on the orange curve by -2.3. And we end up with this final orange curve. Bam! Now we add the blue and orange curves together to get this green squiggle. Now we are ready to add the final bias, B sub 3, to the green squiggle. Because we don't yet know the optimal value for B sub 3, we have to give it an initial value. And because bias terms are frequently initialized to 0, we will set B sub 3 equal to 0. Now, adding 0 to all of the y-axis coordinates on the green squiggle leaves it right where it is. However, that means the green squiggle is pretty far from the data that we observed. We can quantify how good the green squiggle fits the data by calculating the sum of the squared residuals. A residual is the difference between the observed and predicted values. For example, this residual is the observed value, 0, minus the predicted value from the green squiggle, -2.6. This residual is the observed value, 1, minus the predicted value from the green squiggle, -1.61. Lastly, this residual is the observed value, 0, minus the predicted value from the green squiggle, -2.61. Now we square each residual and add them all together to get 20.4 for the sum of the squared residuals. So when B sub 3 equals 0, the sum of the squared residuals equals 20.4. And that corresponds to this location on this graph that has the sum of the squared residuals on the y-axis and the bias, B sub 3, on the x-axis. Now, if we increase B sub 3 to 1, then we would add 1 to the y-axis coordinates on the green squiggle and shift the green squiggle up 1. And we end up with shorter residuals. When we do the math, bip, 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 the sum of the squared residuals equals 7.8. And that corresponds to this point on our graph. If we increase B sub 3 to 2, then the sum of the squared residuals equals 1.11. And if we increase B sub 3 to 3, then the sum of the squared residuals equals 0.46. And if we had time to plug in tons of values for B sub 3, we would get this pink curve. And we could find the lowest point, which corresponds to the value for B sub 3 that results in the lowest sum of the squared residuals, here. However, instead of plugging in tons of values to find the lowest point in the pink curve, we use gradient descent to find it relatively quickly. And that means we need to find the derivative of the sum of the squared residuals with respect to B sub 3. Now, remember, the sum of the squared residuals equals the first residual squared plus all of the other squared residuals. Now, because this equation takes up a lot of space, we can make it smaller by using summation notation. The Greek symbol, sigma, tells us to sum things together. And I is an index for the observed and predicted values that starts at 1. And the index goes from 1 to the number of values, n, which in this case is set to 3. So, when I equals 1, we're talking about the first residual. When I equals 2, we're talking about the second residual. And when I equals 3, we are talking about the third residual. Now let's talk a little bit more about the predicted values. Each predicted value comes from the green squiggle. And the green squiggle comes from the last part of the neural network. In other words, The green squiggle is the sum of the blue and orange curves plus b sub 3. Now remember, we want to use gradient descent to optimize b sub 3. And that means we need to take the derivative of the sum of the squared residuals with respect to b sub 3. And because the sum of the squared residuals are linked to b sub 3 by the predicted values, we can use the chain rule to solve for the derivative of the sum of the squared residuals with respect to b sub 3. The chain rule says that the derivative of the sum of the squared residuals with respect to b sub 3 is the derivative of the sum of the squared residuals with respect to the predicted values times the derivative of the predicted values with respect to b sub 3. Now, before we calculate the derivative of the sum of the squared residuals with respect to the predicted values, let's clean up our workspace and move these equations out of the way. Now we can solve for the derivative of the sum of the squared residuals with respect to the predicted values by first substituting in the equation, and then use the chain rule to move the square to the front, and then we multiply that by the derivative of the stuff inside the parentheses with respect to the predicted values, -1. Now we simplify by multiplying 2 by -1. And we have the derivative of the sum of the squared residuals with respect to the predicted values. So let's move that up here. And now we are done with the first part. Now let's solve for the second part, the derivative of the predicted values with respect to b sub 3. We start by plugging in the equation for the predicted values. Remember, the blue and orange curves were created before we got to b sub 3. So the derivative of the blue curve with respect to b sub 3 is 0 because the blue curve is independent of b sub 3. And the derivative of the orange curve with respect to b sub 3 is also 0. Lastly, the derivative of b sub 3 with respect to b sub 3 is 1. Now we just add everything up, and the derivative of the predicted values with respect to b sub 3 is 1. So we multiply the derivative of the sum of the squared residuals with respect to the predicted values by 1. Note, this times 1 part in the equation doesn't do anything, but I'm leaving it in to remind us that the derivative of the sum of the squared residuals with respect to b sub 3 consists of 2 parts. The derivative of the sum of the squared residuals with respect to the predicted values, and the derivative of the predicted values with respect to b sub 3. Bam! And at long last, we have the derivative of the sum of the squared residuals with respect to b sub 3. And that means we can plug this derivative into gradient descent to find the optimal value for b sub 3. So let's move this equation up and show how we can use this equation with gradient descent. Note, if you're not familiar with gradient descent, check out the quest. The link is in the description below. Anyway, first we expand the summation. Then we plug in the observed values and the values predicted by the green squiggle. Remember, we get the predicted values on the green squiggle by running the dosages through the neural network. Now we just do the math and get -15.7. And that corresponds to the slope for when b sub 3 equals 0. Now we plug the slope into the gradient descent equation for step size, and in this example, we'll set the learning rate to 0.1. And that means the step size is -1.57. Now we use the step size to calculate the new value for b sub 3 by plugging in the current value for b sub 3, 0, and the step size, -1.57. And the new value for b sub 3 is 1.57. Changing b sub 3 to 1.57 shifts the green squiggle up, and that shrinks the residuals. Now, plugging in the new predicted values and doing the math gives us negative 6.26, which corresponds to the slope when b sub 3 equals 1.57. Then we calculate the step size and the new value for b sub 3, which is 2.19. Changing b sub 3 to 2.19 shifts the green squiggle up further, and that shrinks the residuals even more. Now we just keep taking steps until the step size is close to 0. And because the step size is close to 0 when b sub 3 equals 2.61, we decide that 2.61 is the optimal value for b sub 3. Double bam! So the main ideas for backpropagation are that when a parameter is unknown, like b sub 3, we use the chain rule to calculate the derivative of the sum of the squared residuals with respect to the unknown parameter, which in this case was b sub 3. Then we initialize the unknown parameter with a number, and in this case we set b sub 3 equal to 0, and used gradient descent to optimize the unknown parameter. Triple bam! In the next StatQuest, we'll show how these ideas can be used to optimize all of the parameters in a neural network. Now it's time for some shameless self-promotion. If you want to review statistics and machine learning offline, check out the StatQuest study guides at statquest.org. There's something for everyone. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, consider contributing to my Patreon campaign, becoming a channel member, buying one or two of my original songs or a t-shirt or a hoodie, or just donate. The links are in the description below. All right, until next time, Quest on!